Hello everyone, welcome to week 6 Water Resources Engineering's recitation. So let's get started with this first problem, 5.5.3. So the problem asks that the pump tries to deliver from the reservoir A to a reservoir B, and the height of the reservoir A is equal to 47.5 meter, and the elevation for the reservoir B is equal to 55.9 meter. Okay, let me rewrite this. Meter. Okay, and the length of this pipeline L is equal to 1050 meter, and the diameter equal to 0.5 meter. And to calculate the friction head load, the problem asks us to use the Recitation friction factor, which you can find the equation at table 3.4. Okay, so what exactly that the problem asks us is to determine the flow rate Q and the velocity V in the pipeline. So we know now we have a pump somewhere in this pipeline to pump the water from reservoir A to reservoir B, and if the flow rate is higher, then we will suffer higher friction head loss. So, but the relationship between the flow rate and the friction head loss is nonlinear. So we need to use a table to calculate it and to try to find the intersection of the energy that provided by the pump and the energy that lost during this transformation in this pipeline. Okay, let's start to do that. So the total energy that we need to transfer the water from A to B, we denote it as HSH, which is equal to the elevation difference between the reservoir A and reservoir B plus the friction head loss in this pipeline. And the friction head loss, we are using the equation that I show here, because the problem already denotes us that we need to use this method to calculate this friction head loss. And the K factor here is equal to 0.0826 times the factor F times L divided by the diameter of the pipeline. And this 0.0826 is for the English unit. Oh, no, for the SI unit. Sorry about that. Okay. And we know that this N equal to 2 as well. So we can start the calculation. And because, as I say, we need to calculate the value for different flow rates, I mean the head loads for different flow rates. So we create the table here. This table that given by the problem is the pump characteristic. So we simply write this Q, different value of the Q, to this table, and we just want to calculate the friction head loss. So let's start with this first row. We have the flow rate equal to 0. So the total energy that can provide by the pound is equal to 91.4. Okay, so we have 91.4 here, and because there's no flow rates in the pipeline, so according to this equation, the friction head loss is equal to 0. And in this problem, we don't consider any minor head loss, so the minor head loss is also 0. So to calculate the total energy that we need from to transfer the water from A to B according to this equation, because the friction head loss here is 0, and the surface difference HS is equal to 55.9 minus 47.5, which is equal to 8.4. So the total energy that we need when the flow rate is 0 is equal to 8.4. Okay, so similarly, we can do for the second row, that's if the flow rate is equal to 0.15, then we need to calculate the friction head loss using the equation that I showed here. And because we already know all the value for this equation, which m is equal to 2, f equal to 0.018 as given by the problem, and the length of the pipeline is equal to 1,650, and the diameter for the pipeline is equal to 0.5. So you can calculate the head loss given the flow rate using this equation and just write down here. So the total energy that we need in this case is this 1.8 plus 8.4, which is equal to 10.2. So we can do that for all flow rates. Then you can plot the curve in the Excel to find out the intersection between the pound characteristic line and this total energy that we need, which is the system curve, and try to find this intersection point. And after you find that intersection point, then we can identify the flow rates that occur in this pipeline. So in this case, the flow rate is equal to 0.75, as we see. The energy provided by the pound is equal to the total energy that we need to transfer the water from reservoir A to reservoir B. Okay, so now we already answered the first question. The flow rate that we need, the flow rate in the pipelines is equal to 0.75 cubic meter per second. Oh, sorry, what's the number again? 0.75. 0.75 cubic meter per second. Okay, this is the first answer for flow rate. And to calculate the velocity is easy because the flow rate is equal to area times velocity. And we know the diameter in this pipeline is circular. So the area is equal to 2 over d squared times pi, which d is equal to 0.5 meter. So we just plug this area into this equation, and the flow rate is equal to 0.75 cubic meter per second. Then you can easily calculate the velocity. So here I just give you the velocity is equal to 3.82 meter per second. Okay. So now we have solved this problem. We find out the flow rate and the velocity that happen in this pipeline to transfer the water from reservoir A to reservoir B. And the core parts to solve this problem is that you need to find the intersection between the pound pump curve, which is usually given by the problem, and the system curve that we need to calculate using the head loss equation that I show on the screen here. And we will utilize this concept in resolve the problem for this recitation, so just keep in mind. Now, let's move on to the next problem. 5.5.7. So here it's really similar to the previous one, but here we have a different section of the pipeline. In the middle section, we have two branches. And we need to determine the flow rate and the pound head in this system, as well as the discharge in this branch 1 and branch 2 in this big C segment. So that's just right now the information that gave by the problem. So the elevation for the reservoir A is equal to 100 feet, and the elevation for reservoir D HD is equal to 150 feet. And we will use the same friction equation to calculate the head loss. And here we note that the factor F is equal to 0.02 for all pipe. And the pipe AB has the length equal to 4,000 feet with a diameter equal to 3 feet. And for the pipe CD, we have length equal to 1,140 feet, and the diameter CD is equal to 3 feet. And for the branch 1, the length equal to 100 feet with diameter equal to 2 feet. For the branch 2, we have the length equal to 500 feet and the diameter equal to 1 feet. Okay. So the first things, because we want to do the similar thing as the previous problem, we want to plot these two curves together to find out the intersection. But because we have too many pipelines here, it's really hard to calculate the head loss in that case. So the method that we're going to use is to find the equivalent pipe to replace these branches. So essentially, we will translate these 3 segments of pipelines into just one representative, and we use that representative to solve this problem. So let's do that. First, we want to find the equivalent pipe to replace the branch 1 and branch 2. So we simply that the diameter of this new pipeline equal to 3 feet. Okay, because 1 is 2, 1 is 2, and 1 is 1. So we just simply assume that the new pipeline have the diameter equal to 3 feet. And have the same factor F, which is also equal to 0.02. And we will use the equation that we used in the previous recitation. So to find the equivalent pipeline, so the DE to the power of 5 divided by vector E times the length of the new pipeline to the power of 1/2 will equal to the branch 1's diameters to the power of 5 divided by friction 1 times the length 1. Similarly, to the power of 1/2 plus okay. So we just put the information for the branch 1 to here and put the information for branch 2 to here. And because we assumed that's the diameter for the equivalent pipe equal to 3 feet, so this number is put here, and also the factor F will assume to be the same with the rest of the pipeline. So this FE, the equivalent pipeline's factor F, is also equal to 0.02. So the only unknown parameter is the length of this equivalent pipeline. So we can easily calculate this LE, and I just give the number, which is equal to 652 feet. Okay, and I just write down a number for your reference. This is also 0.2, 0.02. The length 1 is equal to 100 feet because the branch 1 have the length 100 feet, and length 2 is equal to 500 feet. Okay. Now we have replaced these two branches into just one single pipeline, and the next thing to do is that to replace these three pipeline series into one representative. And because now they all have the diameter equal to 3 feet, 3 feet, and 3 feet, and they all have the factor F equal to 0.02 here. So the equivalent length for the new pipeline that replaced this entire section is just simply plus the length of these three segments together. So equal to L A B plus the equivalent length for the branch BC plus the length CD, and this is 4,000 feet plus 652 feet for this number, and the CD is equal to 1,140 feet. So in total, we have the length equal to 792 feet long. Okay, so now we gather the all information that we need to apply to this table to calculate the intersection. So similarly, from the previous question, we just copy all the flow rates from this pumped characteristic table, and we calculate the corresponding halos and the total energy that we need to transfer the water given the flow rate that are assigned in the first column, and the HS is the elevation difference between these two reservoirs, which is 150 minus 100. So that's why the entire column is equal to 50. Okay. So just to remind you guys how to calculate this flow friction head loss. This HF is equal to K Q square and the K is equal to 0.0252 times F times length divided by the diameter of the pipeline to the power of 5. Okay, so you just apply this equation and then you can calculate this number. And you can plot the pump curve and the system curve that we show here to another curve and try to interpolate this intersection. So in this case, we say that when you interpolate these two curves, then you can find out the flow rates that's equal to 13.5. That the energy provided by the pump will equal to the total energy that we need for the system. So now we have the flow rates for this pipeline. But the question asks us to further solve the pump head that we need and the discharge in this branch 1 and 2. So now I just write down what we have solved. That the flow rate is equal to 13.5. And from this table, we already know that the total energy that we need is equal to 52.2 feet. Okay, so the pump head is also equal to 52.2 feet. Okay, so the remaining parameter that we need to solve is the discharge in branch 1 and branch 2. And how can you solve that? Because this pipeline is in parallel, so the probability that we have is that the water head loss is equal in these two branches. Let me just clean this line out. So we can use this property to solve it. First, we need to find out the friction head loss, the total head loss, which is equal to the friction head loss because we ignore the minor head loss. So the friction head loss in this BC, we can use the equivalent pipe that we calculate in this section to find out the head loss for that segment. So let me just write down the friction head loss. That's too ugly. Friction head loss for the BC segment will equal to 0.0252 times FL divided by D5 to the power of 5 times Q square. And just plug in the value, which F is equal to 0.02. The length for the equivalent pipeline is equal to 652, and the diameter is equal to 3 feet. because we assume the equivalent pipeline have the diameter equal to 3 feet. And for the flow rates, we just solve that is equal to 13.5. So we can calculate that the halos for the BC segment is equal to 0.246 feet. Then we can use this value to calculate the original branches in this BC segment. So let's first calculate the segment, the branch 1, which have the same halos 0.246. That will equal to 0.0252 times 0.02 times 100 times Q1 square divided by 2 to the power of 5. This 100 is the length in branch 1. And this 2 is the diameter for the branch 1. Okay, and this is just the equation here. Okay, so similarly, we can have the equation for the branch 2, which is exactly the same. This is F, right? This is F. The factor F is equal to in all pipeline, but the length and the diameter will be different. And the length is 500 and diameter is 1 feet. And we just plug down the number into here. The length is equal to 500. And the diameter now is equal to 1 feet. Okay, this is length 2, this is diameter 2. So we can use these two equations to solve the flow rates in branch 1 and flow rate in branch 2. That's Q1 is equal to 12.5 CFS. And flow rate in branch 2 is equal to 1 CFS. Okay, so we have solved this problem. And this coefficient is for the English unit. Okay, so it's the same equation that we used in the previous problem for the Darcy-Weisbach friction factor. Okay, so let's move on to the next problem. 5.6.2. Again, it's a really similar problem, but with a slightly different setup. Now, we have a 1.5 feet diameter pipeline. D is equal to 1.5 feet pipeline to convey the water from reservoir A to reservoir B. The length of this pipeline is equal to 13,800 feet. And the elevation difference between this B reservoir and A reservoir is equal to 196 feet, which we denoted as HS. And we neglect the minor losses. We want to determine the flow rate and the energy head. It will flow by the pound if two identical pounds are installed in this pipeline. Okay, so what does that mean? That means the energy provided by the pump is double compared to just using one pump, right? So the only thing that we need to change here is that the characteristic now, this pump energy provided by the pump can just simply times 2. So this becomes 600 and these become 578. These become this number and 50. Okay, so we use the exactly same process as the problem 1 in this recitation to solve this problem, but with the new HP, which is equal to the original pump energy times 2. So similarly, we just copy the flow rates from the pump characteristic table that provided by the problem here, and we double the original energy that can provide by the pump, and we can calculate the corresponding halos using the equation that I show here. The friction halo is equal to K times Q to the power of 2, which K is equal to, this is the English unit, so it's equal to 0.0252 times factor F times L divided by D to the power of 5. Okay, so you know F is equal to 0.02, and you also know the length and the diameter as I show in this figure. Length is equal to 13,800 and the diameter is equal to 1.5 feet. So you can calculate the corresponding halos for each flow rate. Then we know we ignore the minor halos, so this is equal to 0, and the surface difference between the two reservoirs is equal to 196. So we have HS equal to 196 here, and for SH, the total energy for the system is equal to HS plus the friction halos. So simply you plus this, and you get this. You can do that for every row. Then similarly, you can plot the pump curve and the system curve out, and you find out the intersection. And then you can use this intersection to find out the corresponding flow rate. In this case, the flow rate is equal to 15 cubic feet per second, because the energy that can provide by these two identical pumps will equal to the system's requirement. So we say that the flow rate will equal to 15 cubic feet per second, and the pump energy provided by those two identical pumps will equal to 402 feet. Thus, because those pumps are identical, so for pound, energy provided by pound 1 will equal to the energy provided by pound 2. Approximately, that will equal to 201 feet. Okay, so this problem is really similar. The only difference is that we have two identical pumps installed in this pipeline, which we just double the energy that they can provide, and solve the problem with a similar precision to plot these two curves and find out the intersection. Okay, let's move on to the next one. The problem 5.6.5. Again, it's a similar problem, but with a slightly, different variation. Again, we want to deliver the water from reservoir A to reservoir B. That's the elevation for reservoir A is equal to 45.5. For reservoir B is 92.9 meter. The length of this pipeline is 1,860 meter. Diameter is equal to 0.5 meter. And the factor F that we will use to calculate the water head loads is equal to 0.02. Ignore, no, we actually need to include the minor head loads. Let's consider the inlet access swing type of check valve. And we also have the pump characteristic line here. And the problem already tells us if we only use a single pump, the flow rate will equal to 0.5 cubic meter per second, with the pump head equal to 73 meter. So we want to determine the flow rates in the pipeline if two identical pumps are installed in the parallel combination, as well as the flow rates for the pumps, the two identical pumps using the series combination. So basically we consider these two variations. Okay, so we will use the similar calculation, which for the pump in series, the total head provided by the pump will be double. And for the pump using parallel, the flow rate will be double. Okay, that's the two different setup for two pump in series and two pump in parallel. And because here we need to consider the inlet excess and outer minor losses, so the summation of those K, which is the minor losses coefficient, is equal to KE plus KV plus KD. This is the entrance, the valve, and the exit. And their corresponding number are 0.5, 2.5, and 1. So we have the total K equal to, what's the number is it? 4, okay. And we can simply apply to the H minor equal to the K times velocity head. Okay, so the total head loads So this is for this number, and the friction head loss is the same equation that we used in the previous problem, which is this one. And now the total system energy that we need is equal to the friction head loss plus the minor head loss plus the elevation difference between the reservoir A and reservoir B. So this HS is equal to 92.9 minus 45.5, as I show in this figure. So you have this column, and you use this equation, you can calculate the friction head loss corresponding to the given flow rate. And you know the flow rate is equal to area times the velocity. So you can calculate the velocity for every flow rate, then use that velocity with this minor head loss equation that I show here to calculate this column for the minor head loss. And after you have these three columns, then you can calculate this SH, the last column here. And then again, you can just simply plot these two curves into a plot for the pump curve and the system curve and try to find the intersection. And in this case, the intersection is equal to 0.75. So this intersection have the flow rate Q equal to 0.75. This is the case for the two pumps in series. And for the two pumps in parallel, as I said, instead of double this HP, we double the flow rate. And you just follow a similar procedure. You have the same HF column, H minus minor column, and HS column, and then you have the total energy for the system, which is equal to this equation. Okay, so for the parallel case, we can send plus those two curves out, find out the intersection, which is equal to this one, approximately, because the ideal case is that this HP should equal to this HSH. But they are close enough, so we choose the Q to Q equal to 0.6. So we say this is Q in parallel, this is Q in series, and the unit is cubic meter per second. Then we solve the problem. So just quickly review about this problem. The only difference from the previous problem is that we have two identical pumps, one in the parallel combination and one in the series combination. The only difference is that for the pump in series, you double energy head that provided by the pump, and for the parallel case, we double the flow rate, but keeping the same energy that provided by the pump. Okay, here come to our last problem, 5.7.3. It's basically the same problem but different setup. So now we have instead of 2 reservoirs, we have 3 reservoirs in this problem, and that just write down the basic information for those pipeline and the reservoir, and then we will see what the problem want to access. So the problem says that all the piping here have diameter equal to 1 meter. The length of the pipeline of each segment is equal to 1,600 meter. The factor F is equal to 0.02. And we have two identical pumps located at the reservoir A and the junction B. And the problem also says that the elevation for the reservoir A is equal to 26.2, and the elevation for the reservoir D is equal to 33.5 meter. Okay. And what else? And the discharge in a pipe BC is equal to 500 liter per second, which is equal to 0.5 cms. Okay, this is QBC. And now we need to determine the discharge at AB segment and BD. So we say that this QAB is the variable that we try to solve, and we also need to solve for the QBD. However, we can use the mass balance equation to translate this QBD into the presentation of QAB, which is equal to QAB minus 0.5 cm. It's because the flow direction is from A to B to C and B to D. So if there's have 0.5 cms to the reservoir C, then we can know that BD will equal to QAB minus 0.5 because of the mass balance property. Okay, and besides the flow rates, we also need to solve the water surface elevation for this reservoir C. Okay, and we also need to solve the height for each pump. So this is pump 1, this is pump 1, and this is pump 2. Okay, so follow a similar procedure as previous problems. We need to calculate the intersection between the system curve and the pump curve. To do that, we need to first choose one line to calculate that energy balance. So to start with, can we change the color? Yes, we can. Okay, so let's first choose A to B and B to D as our first target. Why? Because in this pipeline, we only have one pump involved. So if that is the case, we can use a similar plot to find this intersection and find out QAB and QAD. QBD. Okay, so that's the things we want to do. And let's start to do that. So to calculate the friction head loads for this pipeline, we use the same equation, which is K times the flow rate to the power m, where the power m is equal to 2 in our case, and K is equal to 0.0826 times factor F times the length divided by the diameter to the power of 5, and this is for SI units. And we know the factor F is equal to 0.02, L is equal to 1600, diameter is equal to 1. So we can know the K value is equal to 2.6432 meter. No. Okay, just a number, it's a factor. Okay, so we have the equation for calculate the water heat. So next things we want to do is to plot this system curve and pump curve out. And we have the pump characteristic showing this table, but we need to translate this unit into CMAs, which basically just divide everything by 1000. Okay, so easily you can use the Excel to to create a table, put the flow rates here, put the corresponding pump head here, and we want to, this is the things that we want to calculate. Okay, and because as you can see, we have two segments here, one is AB and one is BD, and for the QAB, the water head loads for the AB section is equal to KQAB to the power of 2, and for the friction head loads for the BD segment is equal to KQAB minus 0.5 to the power of 2. Okay, so this is a two equation that we will use to calculate these two terms. So anything before 0.5 here is empty because the flow rate cannot be negative. In our definition, the flow is from B to D. So the flow, this QBD can never be negative. Okay, so you just apply that equation and use the flow rates showing the first column. Then you can calculate these two friction head loads for AB section and BD section. After that, we know the elevation difference between the reservoir N and reservoir D is HD minus HA equal to 33.5 minus 26.2, which is equal to 7.3 meter. Okay, so you just write down 7.3 in this column 5. So the system, the total energy that we need for the system can be calculated by summing these three rows together. So the three columns together. So in the first row is 0 plus 7.3, so we have the 7.3 here, and the second row is 0.17 plus 7.3, so you got 7.47. So do similar things. We can populate the rest of the rows by just summing up these three columns together. Okay, let me clean the board a bit. Okay, then we can use Excel to plot the curve out. So the x-axis is the flow rate, this is Q, and the blue line is the pump curve, which this blue line. The y-axis for this blue line is this HP, and we can also plot the system curve, where the y-axis for those for the orange line is this system energy. Then we want to find the value for this intersection, but as we see on these plots, there's no data point at these intersections, so we need to interpolate these points. Okay, so to do that, it's also really simple. You just add another row and place the equation for this part, this part, this part, and this part, and you just need to change the value for the flow rate to test, okay, at which point that we can create the data points that has similar pump head and the system require energy. Okay, this part needs to be close to each other. And for this point, for this problem, from my own experiment, I choose the flow rate equal to 1.07 because there are still small difference, but it's close enough. So I will choose the QAB equal to 1.7 cms. Okay, so we got this QAB. Let me change to a different color. This QAB now is equal to 1.07 cms, and we know the QAB, then we know the QBD, which is QAB minus 0.5. So this becomes 0.57 cms. Next, we still need to solve. Okay, and we also know the pump, the energy provided by the pump one, also from this interpolation. So here is the pump one, 11.25. So this is 11.25. And because we know the flow rates for BC, right? BC is equal to 0.5. So we can simply find out the total water head that provided by the pump 2 by looking at this pump curve. So this 500 divided by 1000 is equal to 0.5. So this is the 19 is the number for the pump 2. Okay, so the only variable that we still don't know is this the elevation for the reservoir C. So let's see how can we get that. We want to use the energy balance equation to find out this HC. To start with, let's try to find out the energy at this junction B. So the energy at the junction B will equal to HA no oh sorry, my computer is a little bit stuck. Okay, let's start again. The energy at the junction B will equal to the energy at reservoir A plus the energy provided by pound 1 minus the friction halos okay, are you accepting with that? You plus the energy here and you plus the energy provided by the pump, but you also have the friction halos in this section AB, so you need to minus that. And we just plugged in the number. The energy at the reservoir A is simply equal to this HA. That means this will equal to 26.2. And the pound 1 already solved that is equal to 11.25 minus the halos. The K is equal to 2.6432 and the flow rate that we just solved is equal to 1.07 to the power 2. Then we can get the energy at the junction B equal to 38.4 meter. And then we can apply the energy balance again for this BC segment to find out the HC. So the energy at C will equal to HC will equal to the total energy at the junction B plus the energy provided by the pound 2 minus the corresponding water halos in the section BC. And we know that EB now is equal to 38.4 plus the energy provided by the pound 2, that's equal to 19 meter, minus the friction halos 2.6432 times QBC. QBC is 0.5 to the power of 2. Then we can get I miscalculated this number. This is not 38. This is just wait a second. My computer. Okay, let's ignore that. This is 34.4238 meter. So this is 34.4238. Okay, so we will have the final answer for HC is equal to 52.76 meter. Okay, let's just go back here and write the answer down. 52.76 meter. Okay, now we have completed solving this problem. So just fresh memory. We have the 3 reservoirs in this problem, and we want to solve the flow rate in AB and BD segment. So to start with, we choose the pipeline A, B, D to plot the system curve and pump curve out to find out the flow rate first, because in this pipeline we only have one pump involved. And after we solve the flow rate, the next thing what we want to do is to solve the HC, the elevation for reservoir C. And to do that, we will need to use the energy balance equation for the pipeline AB and pipeline BC. And for the pump, the energy provided by the pump, we can use the calculated flow rate with the pound characteristic table that provided by the problem. Then we can easily find out the value for HP1 and HP2. Then you just apply the energy balance equation to find out the energy at the junction B, and use the energy balance equation again for the busy segment, and you can find out the energy hit for the reservoir C, which is equal to 52.76 meter. Okay, so we have finished this week's recitation, and hope you have a nice weekend.